Thanks. So my name's Shaddi Hasan, and today I'll be presenting our work scaling community cellular networks with CCM. And this is joint work with my wonderful colleagues Claire Barela, Matt Johnson, Eric Brewer, and Kurtis Heimerl. And so this is a pretty long-term project, so I also want to give a shout out to all the folks who've helped us, including our funders in the Philippines government, Facebook, USAID, and National Science Foundation. Some of the key contributors to the CCM open source project, as well, Omar Ramadan, Matt Ball, Steve Muir, and Yevgeny Makiv. Our partners at University of the Philippines in the Village Base Station team, and our partners at Globe Telecom on the Connect team, and all the anonymous individuals throughout the Philippines who helped us with the deployments that we'll be discussing today. So let's talk about the spread of mobile networks worldwide. According to the GSMA, which is the Industry Association for Mobile Network Operators, there's approximately 5.5 billion unique subscribers on mobile networks today. These represent the primary way that people get access to critical communication services as well as the internet. This is a particularly impressive spread for a technology that's less than 30 years old. Now, at the same time, while the number of subscribers has increased, the footprint of these networks has started to slow down. And so the traditional telcos have expanded the network to the places where it's financially feasible for them to do so. And what this means is that even today, there's about 1.7 billion people worldwide who lack access to mobile broadband, so that means 3G or better, and over 400 million people who still don't have access to basic 2G communications, meaning they can't send a text message or make a phone call. And so there's been a lot of work to figure out how we can expand the reach of communications to these last 400 million people. And one technique that has emerged in recent years is the idea of a community cellular network. And these community cellular networks are cellular networks that are built by and for their users, typically run in a cooperative fashion, and they're optimized for local needs, leveraging local resources to provide locally relevant services, and have shown that they can be sustainable even in extremely hard to serve rural areas. Now, the key thing that's enabled the rise of community cellular networks is the advent of low-cost GSM hardware and open source GSM software that's made the cost of building a basic cellular network accessible to even extremely rural communities. Now, at the same time, we haven't seen that many of these take off because they face significant barriers to entry. If you want to start your own cellular network, you need an identity for your users on the global phone network, so this is a phone number. You need access to a spectrum license because cellular networks run in licensed spectrum, and these typically cost billions of dollars and are allocated on a nationwide basis. In addition, you need some form of interconnection agreements and other operating licenses to exchange your traffic with other cellular networks in the world. And so these are all resources that the incumbent telcos have, but a community cellular operator doesn't. And if we think about the rural context, it turns out that the incentives of unconnected communities and telcos are actually well aligned. Telcos would love to have more people on the phone network, so those people can call their subscribers, giving them revenue. And communities would like to be able to build their own cellular infrastructures so they can have access to basic services. So the question that we seek to answer in our paper is, can we combine the scale of telcos on one hand with the reach of community networks on the other and help them interact in a cooperative way? And so we built a system to do this called CommunityCellularManager. It's available on GitHub. And we have evaluated it through a 3-year deployment of the largest set of community cellular networks in the world to date, consisting of 17 sites across the Philippines, serving at the end of last year about 2,800 monthly active people. And we've done this in partnership with Globe Telecom, the largest mobile network operator in the Philippines. So to understand how CCM works, let's take a look at how cellular networks work. So typical cellular networks, or the cellular network architecture as defined by the 3GPP, has 2 broad components. First is the radio access network, and the second is the mobile core network. And you need both of these components to provide service to your users. The mobile core is responsible for providing network services and enforcing network policy. And once you have all this set up, you can light up your network. And so if we imagine we want to have 2 users who are in the same tower in a rural community who want to make a phone call, the way this works is they route their traffic just like you did back in the 1920s through with a switchboard. We have established virtual circuits back to the mobile core. We implement billing and charging and so forth there, and the traffic goes back down to that rural community. Now, this clearly enables scalable and successful networks, but at the same time, it has a number of challenges for the rural community cellular networks that we want to support. First, network services are provided on a global basis, and what services are provided are determined by a nation-scale telecom operator. So there's no flexibility for innovation at the service level in rural communities. Next, this system either works or it doesn't work. It doesn't fail gracefully. And in the rural context in which we work, lots of things break all the time. And finally, modifying the configuration and the setup of the mobile core or exposing it to rural communities would be really expensive. It's a critical piece of infrastructure for the mobile network operator. So this brings us to the key design principle behind CCM, which means we need to centralize management to allow the telco to share those spectrum, identity, and interconnection resources with the community networks, while we decentralize the provision of network services. So before I go on, I would just want to highlight, I'm going to talk about voice and SMS a lot because CCM is 2G. And from prior work, we know that in these rural communities, the plurality of devices that people use only support 2G today, and LTE and 5G and more recent technologies simply aren't relevant yet. Though we'll talk about how our work can extend to those towards the end. So in a CCM network, the architecture consists of the following. We introduce the CCM client, which you can think of as essentially a micro-scale mobile core that lives in every single rural community. And the CCM client is responsible for all the provision of network services and enforcement of network policy. Next, we introduce the Ccm Controller, which runs on a public cloud infrastructure. The CCM clients connect to the Ccm Controller over the public internet, and the Ccm Controller is connected directly to the telco's network. To provide service to rural communities, the telco loads a block of phone numbers as well as a spectrum allocation into the Ccm Controller, and the Ccm Controller allocates those resources according to the telco's requirements across community networks. So in this model, if we want to have a phone call that takes place in a single rural community, we can handle all of that traffic at the Ccm client. And we go into detail about exactly how these components work in our paper if you want to learn more. If we want to send traffic to the outside world, though, we still need to send it back to the telco, and we use the Ccm Controller to mediate that interaction. Now we get a number of nice properties from this architecture. First, if we were to say lose our connection from the rural community back to the internet, we're still able to handle local traffic to the extent possible. Next, because each Ccm client is responsible for implementing its own network policy, this introduces the idea that we can have multiple administrative domains all managed by the same Ccm controller. And so different groups of communities could determine what services they want to offer within their networks. Now, when we move to this architecture, we've introduced a new problem for ourselves, and that's how we manage state. And so there's two key types of state in our architecture. The first is per site state, and the second is per subscriber state, most critically billing state. So the mechanism we use for state synchronization in CCM is what we call the check-in. And so every minute, every Ccm client sends an HTTP request to the Ccm controller consisting of the status of that site. So these are things like the temperature, the number of users that are active in the site, and any user activity that's taken place since the last check-in. And the controller responds with the desired configuration state of that site, as well as a list of subscribers that the site is expected to be able to serve. Now, as you can imagine, the configuration of a rural cellular site and its list of subscribers doesn't change very often. So we don't want to have to send this every single minute, and we want to optimize the amount of overhead that we have in our system. So to do this, the client and the controller keep track of the last exchanged configuration. And so because our check-in is broken into sections, what we can do is keep track of a hash of the contents of each section of our check-in, and then on every single check-in request, when the controller generates a new set of configuration, it can see whether or not it matches what the client last received. And by doing so, we can identify if there's been a change and only send the difference between the last sent configuration and the new one. The next piece that we have is the subscriber state. And because CCM implements a simple prepaid billing system which matches what users expect in the Philippines, we're able to limit the number of the set of operations in our system to only commutative operations, meaning we could easily represent this with a convergent replicated data site. And so what we do is we keep track on a per site basis of the balance activity on each site. And so when a user makes a phone call, for example, using 50 credits, we can decrement it on one site. And if the user were to move to a second site, this billing state would be replicated through the check-in mechanism, and the user could perform activities there independently of the first site. And this doesn't require any coordination between the two. So now that we understand how CCM works, let's talk a bit about our deployment. So as I mentioned, we've deployed 17 sites across the Philippines, and these are broadly broken into two groups. The first are what we call the UP sites and are deployed by our partners at the University of the Philippines, and these are all in the Aurora province. The second are a group of sites built by Globe Telecom and one of their NGO partners, and these are deployed elsewhere in the Philippines. Now, all of these sites run the same version of the CCM client, and they all operate under the control of a Ccm controller that's operated by Globe in Manila. And so if we take a look at the usage history of our sites, we see quite a few users over time. And across the scope of our deployment, users have made over 50,000 hours worth of calls and sent or received more than 3 million text messages. So clearly the system is well utilized. Now, to give you a sense of what a rural site looks like in our deployment, I want you to take a look at this picture. So you see a familiar looking tower, but there's some other components that you wouldn't see in a cell phone site here in Boston. So in these rural locations that don't have connectivity, they also usually don't have reliable power. So we have to supply our own, typically done with solar in our deployments, and that means we need to bring our own battery bank as well. In addition, there's no existing fixed infrastructure to use for backhaul, so we have to supply that too, and we use VSAT, which is a form of satellite internet, to provide that service to each site. And each VSAT link is quite expensive for bandwidth, and so we provision each site with 256 kilobits of satellite capacity. So this graph here shows the uptime history of each of our sites, and the way you can read it is that every line represents the history of a single site, and every dot represents whether that site was online or offline during the course of an hour over its lifetime. And so we define online to mean that we were receiving check-ins from the site as expected for the duration of the hour. And if we didn't receive check-ins as expected for any point within that hour, we'll mark it as offline. And we do this in our analysis on a minute-by-minute basis. Here it's just reflected on a per-hour basis for easier comprehension. And so what you can see is when we alternate in these kind of purplish areas between red and blue, that indicates that we have lots of intermittent outages within our network. Now, some of these are due to weather, for example. Some of these are intentional because some sites have to be turned off on a regular basis to conserve power. And we also have some periods of extended outage, typically due to hardware failure. And the key thing to take away here is that these rural sites are down quite a bit due to reasons largely outside of the software's control. And so to drill into why these sites go down, unfortunately our main view into the sites is what we see from the controller. And so we only have ground truth collected by humans for the UP sites, which our members of our research team have access to on an operational basis. And there's really five main components of why sites go down. We can have backhaul failure, we can have power failures, the hardware itself could overheat or go bad for some reason, and we have RF failures, like water getting into a cable. Once in a while, CCM has a bug. But fortunately, that's not very often. The primary reason that we have outages in these sites is due to backhaul failures. And this kind of makes sense if you've ever used satellite internet before. It's susceptible to rain fade, and we're in the tropics. We get typhoons and stuff in the Philippines, so the systems go down quite frequently. But fortunately, these backhaul failures are typically intermittent, and this is exactly what we address by disconnected operation. Now, we can do an analysis of how beneficial our implementation of disconnected operation support is by looking at the call records that we get from sites when they come back online. So we know when sites are not sending check-ins, but if we see activity on those sites, we know they were actually online and serving local traffic. And from our analysis, we find that we're able to support an additional 19% of local call and SMS traffic, as well as, importantly, 16% of additional credit transfers. And these are particularly important in our deployment because credit transfers are the primary mechanism by which users get airtime on the network. They'll go to a local shopkeeper and use a locally hosted SMS credit transfer app to buy airtime. And so this represents local economic activity within each community. Now, supporting disconnected operation has the cost of the overhead of our check-ins. So here we look at the overhead that brings in. This is a CDF showing the size of the requests and the responses. And a median check-in size is less than 3 kilobytes, which is essentially negligible on our network. And while the tails are significantly larger, almost 400 kilobytes, we find that our optimization is quite effective. It reduces the total size by over 90%. And in practice, we find that this amount of overhead is still pretty manageable. The other thing that we were able to do in our deployment is implement a variety of local services specific to the UP sites. So these are services that the globe sites don't have access to. And like I mentioned, the Philippines, especially the Aurora province where these sites are, gets hit by typhoons. And so building in the ability for local communities to repair the sites themselves turned out to be quite important. So when a typhoon's coming, they'll take down the site, pack it away, and then build it back up later on. And there's no telco technician to come do this for them. So we built a repair manual SMS app, an outage hotline, and some promotional billing software to support a randomized control trial that our partners at University of the Philippines are working on as well. So now that we've built this, what's next? So LTE eventually will become relevant, and it changes many things, if not everything. But some of the key things that it changes are the barriers to entry for community networks. LTE is data-centric, and so that means that to provide service, a community cellular network looks a lot like a small ISP. You don't need phone numbers for identity anymore, you just need IP addresses. So that barrier goes away. And while LTE networks still require licensed spectrum in which to operate, unlike GSM, which only runs in about 4 bands worldwide, LTE networks run in dozens of bands, some of which, like the CBRS band in the United States, are specifically designed to support shared spectrum or lightly licensed access. And finally, the interconnection agreements for a community LTE network are fairly straightforward as well, and the operating requirements for running a data network compared to a voice or SMS network in most jurisdictions are significantly lower. And we've already seen LTE being adopted by the types of actors that are very similar to the community networks that we've been supporting in this deployment. As early as 2017, wireless ISPs have been deploying fixed broadband with LTE. And just this year, some members of our team at the University of Washington deployed one of the first community LTE networks in Indonesia. There's also a proliferation of open source LTE software that's come into existence in recent years. So just this week, Facebook released Magma, which is a distributed LTE core network that is similar in architecture to CCM. And my colleagues at the University of Washington are developing Colti, which is specifically designed to support community deployments of LTE. There's also open source open source core networks with more traditional architectures with the Open Air Interface core network and NextDPC. So to conclude, in this talk, we've presented CommunityCellularManager, which is our system that enables scalable community cellular networks. It provides autonomy for the community cellular networks to implement their own services, and its performance degrades gracefully in the face of failures. We've demonstrated a system that can enable a cooperative interaction between large-scale telcos and community networks, and is currently being used to support the largest deployment of community cellular networks to date. Our code's on GitHub, and I'm looking forward to taking your questions. Thanks.
Great talk. So what would it take to reduce the dependence on VSAT? Like, for instance, just connect wirelessly to some very long-range base station, or could Elon Musk's low Earth orbit satellites help in this?
Yeah, that's a great question. So one of the tricks that is particularly relevant for GSM networks, which have very precise timing requirements, is that by moving all of the network policy to the edge and terminating the GSM signaling at the edge, we can separate the access network transport requirements from the fabric, if you will. And so one of our deployments actually in Aurora uses like a directional antenna to get backhaul from a cellular site kind of far away. There's been plenty of prior work in widely deployed long-distance Wi-Fi applications. And there's actually a lot of cool stuff going on in the geosynchronous satellite space that's reducing the cost of satellite connectivity that potentially could start to support data applications as well.
So you think that wireless backhaul is feasible?
It's completely feasible, but the backhaul problem is largely, that's the real challenge of moving this model from supporting GSM, which has basically trivial bandwidth requirements, to supporting data. There's lots of technologies, and putting them together is really more of a business question than a technical one.
Cool stuff. So actually, I guess maybe I had a similar kind of question. So I guess it seemed like the biggest problem right now is the satellite links are terrible, right? So I was wondering is like what are like the local people or what's the infrastructure doing to sort of react to that? I think I can imagine things like local content caching, right? Say, okay, there's been cases where you say, like, I'll cache Wikipedia and put it here, so at least you have Wikipedia when internet is down? Or are there like developments where people are developing like local apps, like okay, whatever, WhatsApp local, where you can still talk to people in your neighborhood rather than having to go to a cloud server and so on?
Yes.
I'm just trying to see like what are the responses that you've seen to this disconnected operation, or is that like sort of work in progress and so on?
So there's a lot of work on like applications in disconnection tolerant environments. And one of the nice things about focusing on voice and SMS is all the content is locally generated. And so when people call each other, we just kind of support that. But somewhat surprisingly, people are annoyed that the sites aren't more reliable. Like, it's not just because folks don't have connectivity in these locations that they've used real, reliable, production-grade phone networks before. And so they know what to expect. And while we have a couple quotes in our paper, and while folks are excited to have connectivity early on and claim they don't care about low reliability, as the deployment rolls on, they express annoyance. So improving the reliability of backhaul is definitely an area for open work.
Thank you.
Hey, Talal from NYU. I remember Rhizomatica in Mexico was doing multiple sites also, and you were working with them also. So is architecturally their solution different from your solution?
That's a great question. So for context, Rhizomatica is another community network that runs in Mexico. We had some pictures from their deployments earlier in the talk. They use a fairly different architecture where every single site in their deployment is completely independent, and their users have kind of local extensions. So they don't have, there's not a one-to-one mapping between a global identity, like in our networks, and a single user. So every site will have a handful of globally routable phone numbers, and an external user would call into that and then dial an extension from there like you were calling like an enterprise or something. But we're largely using the same underlying open source GSM stacks. So right. CCM supports the two primary ones, OpenBTS and Osmocom. They run on Osmocom. Yeah. But they represent a kind of different point in the design space.
Great work, man.
Thanks.
Hi, Ikalin from University of Michigan. Just curious, how is billing handled when you have multiple CCM clients disconnected from the controller and your users handing over from one client to another client?
Yeah, that's a great question. So there's two ways you can handle this. You can basically like cap how much spend can take place in disconnected mode. Our partners at Globe decided to make a policy decision that they'll allow double spend, because that's the risk that you run. This isn't actually a problem in practice, because as you may have seen from our deployment map, most of these sites are located like hours apart. And so it's really about supporting islands of coverage. And so there's no handovers can take place between a CCM client because you'd run out of coverage. Now, you could have multiple sites all connected to the same CCM client, and we support mobility that way. But in the rural context, you just don't really have that kind of wide area mobility that you need to support.
Thank you.
Thanks.